When you look at a graph, it might just seem like a bunch of lines. But what if I told you it's actually telling a story of motion? Every single line, every angle, it's a clue. In this explainer, we're going to learn how to read that story. And we'll kick things off with a little puzzle. Okay, check this out. We've got two lines here, line A and line B. Imagine they represent two different journeys. Now, one of them is definitely moving faster than the other. The big question is, which one? Don't worry, by the time we're done here, you'll be able to tell in a heartbeat.
So, how do we solve this? Well, the answer lies in just one single powerful idea. It's the key that unlocks this entire language of motion. And that key is the slope.
All right, so what exactly is slope? The easiest way to think about it is just steepness. How steep is that line? Because on a position time graph like this one, that steepness isn't just some random detail. It literally is the object's speed. So the rule is simple. The steeper the line, the faster it's going. Okay, but how do we put a number on that steepness? Well, the formula is actually super simple. The slope is just the change in position, how far you went, divided by the change in time, how long it took to get there. You probably heard this back in math class as rise over run. And in our case, the rise is how much your position changed, and the run is how much time went by. So we've got the formula, which is great. But what does all this actually look like on the graph? Let's break down the different kinds of lines you're going to see and what they mean.
This is where it gets really cool, because we're translating abstract lines into actual movement. A zero slope, that flat horizontal line, that's you standing perfectly still. See? Time is ticking by, but your position isn't changing one bit. Now, a positive slope means you're moving forward away from where you started. A negative slope? Simple. You're just moving backward towards your starting point. But here's the most important part, the steepness. A really steep line means you're sprinting. A gentle, shallow line, you're just taking a nice, easy stroll. Oh, and a little bonus tip for you. If you ever see a line that's curved, that means the speed itself is changing. We call that acceleration, but that's a whole other story. I love this because it just perfectly sums up the big idea here. Just imagine the line on the graph is a hill. The steeper that hill, the faster your journey, right? It's the perfect way to remember how this all works. Okay, so we've got the visual idea down. Now let's get our hands dirty with a little bit of math. Don't worry, it's easy. We're going to walk through a quick calculation together to see how we can turn one of these lines into an actual real-world speed. So let's imagine we're tracking something. It starts at the 2-meter mark and ends up at the 10-meter mark. And if we look at our stopwatch, that whole trip took it from the 1-second mark to the 5-second mark. So the question is, exactly how fast was it going? Let's figure it out. It's just a 3-step process, super straightforward. First up, we need the change in position. Well, it went from 2 meters to 10 meters, so that's a difference of 8 meters. Easy. Next, the change in time. It went from 1 second to 5 seconds, so that's a total of 4 seconds. And for the last step, we just divide the distance by the time. And boom, there's our answer. 8 meters divided by 4 seconds gets us 2 meters per second. Now, that's not just some random number. It tells us something really specific. For every single second that ticked by, our object moved exactly 2 meters forward. That's its speed. Simple as that. All right, we've got all the pieces of the puzzle. We get the concept, we've done the math. So let's circle all the way back to that very first question we started with. So which line represents the faster motion? I bet you know it now. It's gotta be line A. Why? Because its slope is way steeper. That means it's covering more ground in the same amount of time. If we actually did the math for both lines, the number we'd get for line A would be bigger than the number for line B. A bigger slope value just means a higher speed. It really is that straightforward. Now, I know this might feel like just a little exercise from a physics class, but this is a really big deal. This is the fundamental language of physics, of data science. It's how we can look at data and instantly visualize speed. Just picture it. The graph for an Olympic sprinter would be almost a vertical line. It's so steep. Compare that to a graph of someone just casually walking their dog. That would be a very gentle slope. And this is used everywhere. Scientists use this exact idea to analyze traffic on a highway or even track the migration of whales across the ocean. It's all about turning a mountain of data into a story you can see at a glance. So let me leave you with one final question to chew on. What would a position time graph of your day look like? Think about it. You'd probably have these long, flat sections when you're sitting at your desk or watching TV, right? Then maybe some gentle slopes when you're walking to the kitchen,
And what about that time you had to sprint to catch the bus? That would be a super steep line. The whole story of your day, your movement, can be told with these simple lines. Pretty cool to think about, isn't it?